Okay, this will be the lecture for Chapter 17, and we will be talking about how we can change phases between solids, liquids, and gases. So kind of where we're going to go today is we're going to talk about the phases of matter, solids, liquids, and gases, and how we kind of go between the three of those. One thing to keep in mind is I really care about where the energy is going for these in these phases of matter, and we'll talk about how evaporation is a cooling process, condensation is a warming process, boiling, believe it or not, is going to be a cooling process, and I'll just put some jargon to the names of melting and freezing. And again, I really care about where the energy is going on for these changes of phase, and we'll talk about how much energy is involved to break the bonds of a solid and turn it into a liquid, and break the bonds of a liquid turn it into a gas. Now you're probably pretty tired of seeing this slide, but solids, liquids, and gases, kind of the difference between those. Solids have a definite volume and shape. Liquids have a definite volume but not a definite shape, and gases don't have a definite volume or shape. And you kind of think of water, for example. The phases of water that we have, we're going to have the solid phase, we're going to have ice. We're going to have the liquid phase, we're going to have just liquid water. And the gaseous phase, we're just going to have essentially steam. Now, the exact state is going to depend on the temperature. Now, I'm just going to talk very briefly about the phases of matter, starting with gas. I'll talk about liquids and I'll talk about solids, and I really want you to pay attention to where the chemical bonds are, because there's energy in those chemical bonds. So, water in the gaseous phase is going to be steam, although technically you really can't see steam, so you're not quite looking at the gaseous phase of water when you're looking at steam, but close enough. And we're going to have independent molecules, and that's going to be kind of the key thing to keep in mind. And these independent molecules are definitely in motion because they have some thermal energy. So if you think about water, H2O, it's going to be 2 hydrogens, 1 oxygen, and we're going to have this kind of individual molecules just kind of whizzing around just like this. And it's going to be something that we can compress. You can blow steam into a 2-liter bottle and squeeze it down to a different volume. So it's not going to have a definite shape, and it's not going to have a definite volume as well. Water as a liquid, you can kind of think of these as the same thing. It's going to be water molecules, and these guys are loosely bound into loops or chains that can kind of slide up against each other. And these things are in motion because they have some energy. So you can kind of think of these are all little water molecules, and there's some bonds here, some bonds here, bonds here. But this guy can kind of slide around, and they are also kind of in motion. That allows it to not have a definite shape, but it's going to fill a volume. You can't really compress water very easily. Keep in mind, loosely bound to other molecules, so that means that there's some energy inside of those chemical bonds. Lastly, water as a solid. Think ice, think snowflakes, stuff like that. Here we have molecules that are tightly bound into a nice orderly structure. So tightly bound is kind of the important word to keep in mind, because there's going to be energy in those chemical bonds, and there's going to be a lot of energy in those chemical bonds. Keep in mind that these guys are still in motion because they have thermal energy, so you can kind of think of having a bunch of molecules that are connected by springs, and these springs kind of represent chemical bonds, and these guys are kind of wiggling back and forth because they do have some energy, and it's going to be fairly incompressible, so you can't very easily change the shape or the volume. So here I kind of have a schematic of just some ice and a crystal lattice, and you can see it really is quite orderly and kind of even pretty to look at. Now, again, what I really care about is where is the energy? And so let's talk about the phases of matter and how we go from, say, some ice into some liquid into some gas, and we could even go into the 4th stage of matter. When we go from the solid phase, say some ice, and we melt it into some water, we're going from a solid to liquid, and it takes energy to go from a solid down to a liquid. So we have to add energy to break down those chemical bonds, that nice tight orderly structure that you had. When we go from the liquid phase to the gaseous phase, we're taking chemical bonds and we're adding energy, and we're breaking those chemical bonds to turn water into a gas. So it takes energy to do this. And actually, if we go from the gaseous phase to the plasma phase, then it takes even more energy because we're disassociating those electrons from the nucleus. The exact phase is going to depend on the pressure and the temperature, and I'm not going to talk about pressure so awful much, but it definitely is going to depend on temperature. We know that we're going to have 0 degrees Celsius is kind of the breaking point for where we have a liquid versus a gas, or a liquid versus a solid, and we know that water is going to boil at 100 degrees Celsius, so it definitely is going to depend on temperature. Now let's just have to get a little bit of jargon out of the way. As we talk about going from a solid into a liquid and into a gas, I just want to put some names to what's going on right here. Keep in mind that I really care about where the energy is. When we go from a solid to a liquid, we're going to call that melting. And when we go from a liquid to a gas, then we're going to call that evaporation. And when we kind of go in reverse, when we go from a gas to a liquid, we're going to call that condensation. And when we go from a liquid to a solid, we're just going to call that freezing. Now, two phase transitions that you may not know is when we go from a solid directly into a gas, we're going to call that sublimation. And we can also go from a gas directly to a solid, and we're going to call that deposition. Now, keep in mind, I really care about where the energy is. And if we go from a solid to a liquid, if we melt, then we have to add energy to that. If we go from a liquid to a gas, we have to add energy. If you want to boil water, you have to put it on the stove. So when the arrows kind of go in this direction, we know that we need to add energy to the substance. And when we go in this direction right over here, then we're going to take energy away. So just kind of draw the picture and say, am I going in this direction or am I going in this direction? You have to add energy in this direction, take energy away in this direction, and that does apply to sublimation and deposition as well. Now I just want to give you some examples of the two that you may not be as familiar with. Let's think about frost on your windows. What does not happen is liquid or gaseous water vapor in the atmosphere does not hit your window and then melt and then freeze. You have a nice pretty pattern like you see right here. This is going to be an example of water going directly from the gaseous phase into the solid phase, and we're going to call that deposition. And an example of what's going on inside your freezer, if you've ever had an ice cube that's kind of been in the back for a long time and it gets smaller and smaller and smaller and smaller, it tends to at some point disappear. That's going to be an example of water going from the solid phase directly into the gaseous phase. It doesn't just melt or anything like that. So that's going to be an example of sublimation. Another example of sublimation would be mothballs. If you ever look in the back of your grandmother's closet, you're going to see some mothballs. You go back like a month or two later, and the mothball is going to be a little bit smaller, and smaller still, and at some point it just kind of goes away. Examples of sublimation. Okay, now I want to talk a little bit more about evaporation and condensation, and I want you to pay kind of attention to where the energy is. If we think about evaporation, that's when we're going from a liquid to a gas. So if we have just some liquid water over here, so this is going to be my liquid water, and right over here we're going to have some gaseous water, then what happens when something evaporates is, if you think about it, these guys are all in motion, and suppose this guy is moving in this direction, this water molecule is moving in this direction, that water molecule is moving in that direction, and they're all bumping into one another, kind of exchanging energy. If they all run into each other right here, let's just say, and all of that energy gets transferred to one of the molecules, I'm going to pick this guy right over here, then this guy might go flying off into the gaseous phase, and the energy has essentially left the liquid and gone into the gas. All the energy's kind of gone in this direction right over here. So if something's allowed to evaporate purely on its own, then it's going to essentially cool off. Now this slide right here pretty much just has everything in text what I said on the last slide. Keep in mind that evaporation is going to be a cooling process when we think about it from the liquid standpoint. We're going to have molecules that are just kind of bumping into one another. They're going to be exchanging energy, and when one of the most energetic molecules happens to escape the liquid, break some chemical bonds, and becomes a gas, kind of the net result is the average kinetic energy of the liquid is going to go down. So evaporation is going to be a cooling process on its own. Now, when it comes to evaporation, I'm probably not telling you anything that you don't already know. We know that when do we sweat? Well, we sweat when it's hot outside, and sweating is going to be really important to cooling our bodies down. You know, kind of what happens is if you're too hot, then your body's going to sweat, it's going to perspire, and that water is going to go somewhere. It's going to go into the air. So as the water evaporates, then what's happening is it's kind of cooling our body, and it's kind of how we maintain a nice steady body temperature. Not all animals have these sweat glands, and if you kind of ever wondered why pigs wallow in the mud, kind of what they're doing is they're doing the same thing. They're getting all this water onto their backs, that water is evaporating, and it's kind of cooling them down. So pigs are actually pretty smart. Just kind of an aside, sublimation is also going to be a cooling process. It's when we go directly from a solid to a gas. And so if here we have a solid, here we have a liquid, and here we have the gas. As long as we're going in this direction right over there, then essentially it takes energy for that to happen. So it's going to be a cooling process when we talk about the solid itself. And examples, I've already talked about mothballs, I've talked about water in the fridge. Another fun example would be dry ice. End of the day, however, sublimation is going to be a cooling process when it comes to talking about the solid. Now, condensation is pretty much the opposite of evaporation. If you think of having some water in the form of a gas, and these water molecules are all in motion, kind of going like this, when this water molecule right over here strikes the surface and it sticks to it, then what's happening is we're essentially adding energy into the liquid, so it's going to be warming it up. So we're increasing the energy of the liquid, going to be warming it up. This just kind of says in text what I said verbally on the previous slide. So condensation, essentially we're adding energy from a gas into a liquid, so it's going to increase the temperature of the liquid. And kind of an interesting aside, if you think about having steam, or if you had 100 degrees Celsius gaseous water vapor, when that steam hits your skin, then it's going to condense and it's going to transfer energy to your skin, and it's going to be pretty damaging. All the energy is going to go into your skin. Kind of more interesting is that that's going to be more damaging than just 100 degrees Celsius boiling water. One thing to kind of keep in mind about condensation and evaporation is they're both actually happening at the same time. However, if one of them happens faster than the other one, then you may feel warmer or cooler. For example, in a dry city, then what's going to happen is there's going to be some evaporation and there's going to be some condensation, but because it's dry out, the rate of evaporation is going to be larger than the rate of condensation, and so you're going to feel colder. Kind of an example of that is if you're in Las Vegas, Nevada, in a casino, and you jump into the pool. It's a really dry city there. When you get out, it may be really warm outside, but you're going to feel cold as the water evaporates off of you. Kind of conversely, if you go into the deep south where it's really humid out, the rate of evaporation is going to be smaller than the rate of condensation. You have all this water vapor in the air, and so you're going to tend to feel warmer, and that's really not a very good thing. Kind of another example is have you ever wondered why if you have a cold Coke and you set it out into some warm humid air, what's going to happen is it's going to condense. What happens when it condenses is air is going to bump into it. It's going to cool off the air molecules. It's going to slow them down, and they're going to strike the cold surface, and it's going to get some condensation. Where does the energy go when we have condensation? Well, it's going to go into the liquid, so it's going to warm up your cold Coke. Now let's just talk really quickly about condensation happening in the atmosphere. When is it most likely to happen? Well, if you think about it, if you had a water molecule right here and a water molecule right here, and these are in the gaseous phase, so they're just kind of moving around. When they're going relatively fast, so draw this guy kind of like this and draw this guy kind of like that, that's going to be essentially when they're going to be relatively warm. And these guys have a lot of energy. They're more likely to bounce into or run into each other and then bounce off of each other. But as we lower the temperature, essentially what we're doing is we're lowering the speed, molecules are moving more slowly, and slowly moving water molecules are more likely to stick together. And we tend to see this, for example, in fogs and clouds, because when air rises, it tends to cool off. It's going to slow down the water molecules, and they're more likely to coalesce, which is a fancy word for stick together, upon collision when it's cold, when they're cold out. They have less energy. Now, just take a second and think about this. I'm sure everyone has done this, where you're in the shower and you get out and you feel pretty cold, and so you hop back in and you towel off in there. Kind of the reason for that is, if you think about it, right over here inside of the shower we have a lot of water vapor, and right out here we don't have a lot of water vapor. So when you step out of the tub, kind of like this, then what's happening is we're getting a lot of evaporation. When you jump back into the tub, well, there's a lot of water molecules here. These water molecules are in motion, they're kind of bumping into you, and there tends to be a lot of condensation. So when you jump out, there's going to be a lot of evaporation. When you jump back in, there's going to be a lot of condensation. So probably